Well, students, in the last class, we have studied rectangle rule in the numerical integration section. In this lecture, we will take up our next quadrature rule called the trapezoidal rule. Let us recall that the quadrature rules that we are interested in can be written in the general form like this, that is f of x naught w naught plus f of x1 w1 plus dash 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 plus f of xn wn, where wi's are the weights obtained by integrating the Lagrange polynomial Li of x over the interval a to b in which we are interested in performing our integration. Now, as far as the trapezoidal rule is concerned, we will take n is equal to 1 in this general formula. Thereby, we will be having only two terms in this sum, which is precisely obtained by integrating the polynomial p1 of x, which interpolates the function f at the points x0 and x1. So let us try to obtain explicitly how this formula will look like. For that, we have to integrate this polynomial p1 of x. And in this expression, let us take x0 equal to a and x1 equal to b and perform this integral that leads to the expression b minus a into f of a plus f of b by 2. And this is the required formula for the trapezoidal rule. The geometrical interpretation of the trapezoidal rule is something very similar to the rectangle rule. If you recall, suppose we are interested in finding the integral of the function f of x whose graph is like this, and we are interested in integrating between a and b, then we want the area under the graph of the function f of x between the two lines x equal to a and x equal to b, right? Now what we did is, instead of having f of x, we have p1 of x, which is nothing but the line joining these 2 points a comma f of a and b comma f of b, right? That is the polynomial p1 of x, and thereby we have the area under this line, which is bounded by the lines x equal to a and x equal to b. Thereby, we are having the mathematical error in the trapezoidal rule, which is precisely the area between the line p1 of x and the graph f of x, right? By definition, the mathematical error involved in the trapezoidal rule, which is denoted by MET of f, is given by the difference between the exact value I of f and the approximate value, the integral of the first degree polynomial p1 of x. Let us get an expression for the mathematical error. For this, we need to assume that f is a C2 function defined on the interval AB. Then the mathematical error MT of f of the trapezoidal rule can be written as minus f double dash of eta into b minus a cubed by 12, where eta is some unknown number in the interval a comma b. Let us see how to derive this expression for the mathematical error of the trapezoidal rule. The basic idea is very much similar to what we have discussed in the last class. You construct the polynomial interpolating the function f at the nodes a comma b comma some x, where x is some arbitrary number in the interval a comma b. such that x is not equal to a and x is not equal to b. So let's call this as P2 of t, which is obtained by replacing x minus a by t minus a and x minus b by t minus b. Now, since x is one of the interpolating point, if we evaluate P2 at the point x, we will get it as f of x by the interpolation condition. And that is how we are writing here, f of x is equal to the polynomial P2 evaluated at t is equal to x, right? And that is nothing but P1 of x. Remember, this is the polynomial we have used in our integral in order to approximate integral a to b f of x dx, right? Therefore, integral over a to b P1 of x dx is precisely the trapezoidal rule. That is why we have put here the left hand side is the integral over a to b f of x dx. And similarly, when you take the integral on the second term, we get this. And that gives us the mathematical error expression like this. Now we have to somehow rewrite this integrand in the form that leads to our desired expression. Let us see how to handle this term. If you recall from the Hermite-Ginocchi formula, we see that the function say f of x is equal to the second order divided difference of f at the nodes a, b and x is a continuous function, right? And these two are also continuous functions. Therefore, the integrand is a continuous function. That is what we understand. Therefore, we can apply the mean value theorem for integration. Note that x minus a into x minus b is a non-negative function for all x in AB, and therefore we can indeed apply the second mean value theorem for integration, through which we can find a eta in the interval a to b such that the actual integration can be written as f of a comma b comma eta times integral a to b x minus a into x minus b. Now let us recall from the previous chapter that the divided difference of f at the nodes x0, x1 up to xn comma x. It means you have n plus first order divided difference can be written as f of n plus first order derivative of f evaluated at xi of x divided by n plus 1 factorial, where xi of x is some point in the interval a comma b. Recall that it is one of the exercise problems in the previous chapter, which is an important exercise problem. I recommend you to see how to solve this problem. So let us use this formula in the expression that we have derived so far for the mathematical error of the trapezoidal rule, and that gives us f double dash of xi x into, you have to integrate this term, and that gives us b minus a cube by 12. And that is what we wanted to obtain as the mathematical error expression. Sorry, I have missed a minus sign here. It is minus f double dash of xi x into b minus a cube by 12. Maybe in the statement, xi x is denoted by eta. Please note this difference also. And this completes the proof of the theorem. Let us take an example. Let us consider finding the integral of the function 1 by 1 plus x over the interval 0 to 1. You can directly, in fact, find the value of this integral, and that is given by log 2, which is approximately 0.6931. Let us apply trapezoidal rule and see how trapezoidal rule approximates this integral. As per trapezoidal rule, we have b minus a, which is 1, divided by 2 into f of a, where a is 0, plus f of b, where b is 1, and that gives us 0.75. In fact, in this example, we can find the value of the mathematical error explicitly because we have the exact value and also the value obtained from the trapezoidal rule. Therefore, we can directly find the difference between these two, at least up to the decimal digits given in the exact value. The mathematical error is approximately minus 0.0569. Let us try to get the estimate using the expression which we derived in the last theorem. If you recall, in the last theorem, we have derived the expression for the mathematical error as minus f double dash of eta into b minus a cube by 12, right? Let's compute f double dash of eta. F dash of eta is minus 1 by 1 plus x square, and f double dash of eta is therefore given by 2 by 1 plus x, the whole cube, right? Therefore, the mathematical error in the trapezoidal rule in this particular example is given by minus 1 by 6 into 1 plus eta cube. Sorry, these are eta, not x, where eta is the unknown in the interval 0 to 1. So if you use this formula, therefore you cannot find the exact value of the mathematical error. However, we can find the lower and upper bound of this expression, and then we can check whether that bounds respect our exact value. This is just to cross-check the theory and the numerical result. For the lower bound, let us put eta equal to 0, and for the upper bound, we will put eta equal to 1, and thereby we will get the mathematical error in the trapezoidal rule is bounded by minus 1 by 6 and minus 1 by 48. That is, I'm putting eta equal to 0 here, and I'm getting minus 1 by 6, which is the lower bound, and I'm putting eta equal to 1 here, and thereby I'm getting minus 1 by 48, which is the upper bound. We don't know what is exactly eta, but whatever may be the value of eta, your mathematical error will lie between minus 1 by 6 to minus 1 by 48. This is what the theoretical prediction says. But in this particular example, we got the value of mathematical error directly, and that was minus 0.0569. This is a good verification that numerical result is well in agreement with the theoretical prediction. Next, let us derive the composite trapezoidal rule. Let us quickly recall from our previous lecture that to improve the approximation of the quadrature formula, we can also go for the piecewise polynomial approximation to the integrand. In this, we have to first break the interval AB into smaller subintervals and apply the trapezoidal rule in each subinterval. Not only trapezoidal rule, for any quadrature rule, we can follow this idea to obtain the corresponding composite rule. Let us derive the composite trapezoidal rule. Again, we will assume that all the subintervals are of equal length, and the length is given by b minus a by n. It means we have x0, x1 up to xn as nodes, where each xj is given by a plus j into h. With these nodes, we will break our integral a to b f of x dx into smaller integrals evaluated over each subinterval and then sum them up to get the value of our original integral. Now the idea is to put the trapezoidal rule for each of these integrals. That is, we will put the trapezoidal rule formula for the integral xj to xj plus 1 in the previous expression and get the composite rule in this form. This can be rewritten to get the final formula for the composite trapezoidal rule. Again, let us take an example where we will take n is equal to 2, whereby we are breaking the interval a to b as x0 to x1 and x1 to x2, right? So we have two pieces, and in each piece, we will be putting the trapezoidal rule. Let us consider the same integral as we have considered in the last example, that is integral 0 to 1 dx by 1 plus x. If you recall, the exact value of this integral is 0.693149. And let us apply the composite trapezoidal rule with the nodes as x0 equal to 0, x1 equal to 1 by 2, and x2 equal to 1. And you can just substitute all the relevant values in the formula that we have derived in the previous slide. You can see that the value of the integral as per the composite trapezoidal rule with n equal to 2 is given by this number. You can see that this is far better approximation to our exact value than what we got with the trapezoidal rule in the previous example. If you recall, in the trapezoidal rule, we got 0.75. And here we got a pretty better approximation, which involves the error minus 0.0152. If you recall, in the trapezoidal rule, we got minus 0.0569. Let us now learn how to do convergence analysis for composite trapezoidal rule. This is given as an exercise problem in the chapter on numerical integration and differentiation. I think it is the problem number 5 in our notes. We have the interval a to b, and we subdivide this interval into n plus 1 subintervals of equal length with partition as x0, say x1 and so on, xj, xj plus 1, and so on till xn minus 1 and xn, which is equal to b, right? As we know, we intend to put the trapezoidal rule for the integral xj to xj plus 1 f of x dx, right? Where xj plus 1 is xj plus h, which can also be written as a plus j plus 1 h, where h is given by b minus a by 2. So these are the things that we know already when we were developing the composite trapezoidal rule. We will assume that f is twice continuously differentiable on the interval ab. Then the problem says that the mathematical error involved in the composite trapezoidal rule with n plus 1 partition points is given by minus b minus a h square by 12 into f double dash of xi, where xi is some point in the interval a to b. And further, for each n, if you consider this ent of f as a real number, then you can see that we have a sequence of real numbers. And the second part of the problem says that this sequence converges to 0 as n tends to infinity. Each member of this sequence is the error involved in the composite trapezoidal rule with the corresponding partition having n points, right? Therefore, if this sequence is converging to 0, it means that your approximate value of the integral is converging to the exact value. That is what it means. So we call this result as the convergence of the composite trapezoidal rule. Let us prove this result. If you recall, the error in the trapezoidal rule for the integral xj to xj plus 1 f of x dx is given by the mathematical error MET of f is equal to minus h cube by 12 into f double dash of xi, where xi is an unknown point from the interval xj to xj plus 1, right? Now, if you recall, the composite trapezoidal rule is nothing but the sum of the trapezoidal rules applied to each of these subintervals xj to xj plus 1. Therefore, the mathematical error in the composite trapezoidal rule for the interval a to b f of x dx is given by, remember we use the notation et n of f, and that is going to be sigma j equal to 0 to n minus 1 minus h cube by 12 into f double dash of xi j, right? Because for each subinterval you have a xi, therefore it's better to put xi j here, where xi j belongs to the interval xj to xj plus 1, right? We are just applying this formula for the mathematical error in each of the subinterval and then sum them up, right? For psi j belonging to the interval xj to xj plus 1. Wherever possible, you have to write this information. Recall that we have taken h to be b minus a by n. We use this formula for one of the h here and write etn of f is equal to sigma j equal to 0 to n minus 1 h square by 12 into 1h I will write as b minus a by n, and then f double dash of xi j, right? Now this can be written as minus h square by 12 into b minus a, well there is a minus here also, into 1 by n into sigma j equal to 0 to n minus 1 f double dash of xi j. We have assumed that f double dash is twice continuously differentiable on the interval ab, and therefore we can use the intermediate value theorem to see that there exists a xi in the interval ab such that f double dash of xi can be written as 1 by n into sigma k equal to 0 to n minus 1 f double dash of xi k. If you recall, we have done this problem in one of the exercises. I think in exercise 1, we have done this problem. I'm just using this problem and replacing this term by f double dash of xi. Therefore, we can write the error in the composite trapezoidal rule with n plus 1 partition as minus h square by 12 into B minus A into F double dash of xi, right? That is what precisely we want to show here. Well, again, there is a minus sign. Yeah, so the minus sign is also there. So this completes the first part of our problem. To prove the second part, that is convergence, again, we have to use the assumption that F double dash is continuous on the interval a comma b. Therefore, we can find a constant m such that mod f double dash of xi is less than or equal to m for all xi in the interval ab, right? In fact, we can put the closed interval. That is just to dominate this term because we have a variable xi involved in it, which is also not known to us. Therefore, we have to freeze this term in order to get an estimate for the mathematical error in the composite trapezoidal rule. For that purpose, we are using the fact that f double dash is continuous. Then you can see that mod E T n of f is less than or equal to m times b minus a by 12 into h square, right? Now note that h is given by b minus a by n. That shows that as n tends to infinity, h tends to 0, and that implies that the right hand side tends to 0 as n tends to infinity because m is a finite number, b minus a by 12 is also a finite number. Therefore, the right hand side goes to 0 as n tends to infinity, and that implies that E T n of f tends to 0 as n tends to infinity, right? That is what we want to show as the second part of this problem. And this proves the convergence of the composite trapezoidal rule. As far as f is twice continuously differentiable function on the interval on which we want to evaluate the integral f of x dx, you can see that the composite trapezoidal rule always converges to the exact value of this integral. Another interesting application of this inequality is that suppose if I give you an epsilon, some number, say epsilon is equal to 10 to the power of minus 3 or something, and say that if I want my error to be less than this epsilon, how many subintervals that I should have? That is, what is the n that I have to choose? If you ask this question, you can immediately see that the upper bound can be used to find the n such that this error is less than that epsilon. How will you do that? Well, you just impose this condition, m into b minus a by 12 into h square is less than or equal to epsilon you impose, and use the fact that h is equal to b minus a by n, right? And that gives you m into b minus a cube by 12 into 1 by n square. From there, you can find what is the n that you need to achieve the error less than the epsilon that we are given, right? So in that way, this inequality is also very useful.